Welcome to this professional training explainer, electrical schematics reading. This deep dive is designed specifically for you, the master HVAC technician, and it's presented by Level Up HVAC Training. We're going to completely unpack the exact methodologies, frameworks, and visual languages you need to diagnose complex electrical faults with total, absolute precision. Look, as a master tech, you already know your way around a system. That's a given. But let's be real, your ability to efficiently decode these schematics, that's exactly what separates the true experts from the guessers. Presented by Level Up HVAC Training, this explainer is built to take your existing skills and sharpen them, so you can isolate faults faster and way more safely. Let's get right into it. Let's kick things off with a pretty jarring reality. Just 50 milliamps of current passing across the chest is literally enough to stop a human heart. Every single safety decision you make out there in the field traces back to the fact that the human body is a conductor, and the voltages inside an HVAC unit, they are more than enough to be lethal. That's exactly why reading schematics to plan your meter placement is a matter of life and death. You use the schematic to plan your test points without ever guessing, because guessing is exactly how techs get hurt. Okay, here's our blueprint for today. We're going to run through fundamentals and crucial safety, decode schematic symbols, contrast ladder and wiring diagrams, trace power distribution and AC basics, read a full sequence, and then cap it off with some elite pro troubleshooting techniques. All right, Section 1, Fundamentals and Crucial Safety. Before you ever touch a wire, pull a disconnect, or even clip on a meter, we've got to reestablish the absolute non-negotiables. E equals I times R, Ohm's law. It's the foundation of every test. Voltage confirms electrical pressure is arriving. Amperage confirms the load is physically working. But resistance? That's how we safely confirm an open or shorted component with the power completely off. Your schematic is the map for placing those probes safely. Moving on to Section 2, Decoding Schematic Symbols. This is the alphabet of the trade. If you can't read this fluently, you can't read the map. Think about the direct comparison between control and action. You have a control device, like a relay coil designated CR. Then you have the physical action, like a normally open relay contact. That low-voltage coil magnetically pulls the contact closed, allowing high voltage to pass right through. Instantly recognizing that relationship? Absolutely key to moving fast on a call. Similarly, you've got to quickly identify your power converters and protection devices. You have your step-down transformer, taking your line voltage primary and dropping it to your secondary control voltage. And right alongside that, you'll see critical protection devices, like the thermal overload. That symbol usually illustrates a heater element paired with a normally closed contact, tucked right inside a motor to break the circuit if things overheat. Okay, Section 3, Ladder V Wiring Diagrams. We essentially use two very different maps to understand the exact same machine. Knowing which one to pull up is going to save you hours. The wiring diagram, that's your physical map. It shows components and their actual locations with wire colors, plugs, harness layouts. It's messy, but it's what you use to physically find a component in a crowded panel. The ladder diagram, though, strips away all that visual clutter. It reveals the pure logic and sequence of operation. You use the ladder diagram to figure out the why behind a system failure. To read that logic, we have to trace the power. Follow the sequence of how 240-volt split-phase utility power travels. It goes from the service drop right through the sealed meter, into the main panel for distribution, out through your dedicated branch circuit, hitting your disconnect lockout point, and finally landing as a high-voltage supply at the unit's contactor. Next up, Section 4, Power Distribution and AC. Now we look at how that incoming power is protected, sized, and converted. Think of nameplate data as a rapid-fire checklist. MCA sets your minimum wire size. MOP or MOPD is your absolute max fuse or breaker size. And when you're testing loads, just remember, your normal running amps will always be significantly lower than that heavy startup surge of your locked rotor amps. To safely control all that massive high voltage, a transformer steps it down. We rely heavily on those 24-volt industry standards, right? R for power, G for fan, Y for cooling, W for heating, and C for common. This standardization keeps our control wires cheap, universally understood, and perfectly safe to handle while troubleshooting. All right, Section 5, Reading the Full Sequence. Let's put it all together. When you read a ladder schematic, you follow strict top-down rules. You read rung by rung, top to bottom. For each horizontal rung, trace left to right from L1. The absolute golden rule here is that every single switch or control device in series on that rung must be closed for the final load, which is always at the far right rail, to actually run. By following this left to right flow, you can map out exactly when each load energizes and precisely why a safety string might interrupt it. And finally, Section 6, Pro Troubleshooting Techniques. Reading the diagram is really only half the battle. Let's look at how master techs apply this for ruthless field efficiency. When you walk up to a dead unit, I want you to ask these 3 master questions in this exact order. 1. Does the load have both legs of line power? 2. Does the low voltage control signal actually arrive? And 3. Is the physical load itself within factory spec? If you can say, yes, power is there, yes, the signal is there, but no, the load isn't running, well, boom. You've isolated the fault to the load itself before you ever started randomly pulling off panel covers. To answer those questions fast on a complex circuit, we use the half-splitting method. This is an elite diagnostic framework. Instead of testing sequentially from start to finish, you look at your schematic, find the exact electrical midpoint, and test voltage there. Got voltage? The problem is downstream. No voltage? It's upstream. Every single test mathematically eliminates half the remaining circuit. You can literally isolate a fault among 16 separate components in just 4 precise meter tests. It's a total game changer. Then you've got the hopscotch method. When you're dealing with 24-volt control circuits or long strings of safety switches in series, this is what you use. Clip your meter's common lead securely to neutral or C. Then, take your hot lead and probe step by step along the series rung, just hopping toward the load. Where the voltage suddenly disappears, that's exactly where the circuit is broken. It pinpoints the open switch without you unwiring a single thing. Now, mastery isn't built in a day. It takes deliberate practice. So here is your 30-day challenge. On every single service call for the next month, open the panel and find the schematic first. Label the physical components in your head before pulling out your meter. And finally, trace the ladder diagram to predict the exact sequence of operation before you ever restore power. We've covered the symbols, the strict top-down logic, and elite frameworks like half-splitting and hopscotching. Armed with this knowledge from Level Up HVAC Training, the real question is this: how are you going to apply this master blueprint to work smarter, stay safer, and diagnose your very next dead unit with absolute precision? The map is in your hands. Let's get to work.